This is an AQA A-Level Chemistry Year 13 topic. We're looking at carbonyl chemistry. This is video number 5 in a series of 5. And in this video, we're going to focus on nucleophilic addition-elimination mechanisms, also known as acylation reactions. So, I'm going to recommend you pause, have a go at all the activities for yourself, and then review. That way you get to see what's going well and what you might need to focus your attention on. So we've got here a nucleophile is a lone pair donor, a definition that you're hopefully familiar with from other topics, and an electrophile is a lone pair acceptor. So let's move in and take a look at the acyl group itself. Acyl groups can be added to many molecules, and we often do that using acyl chlorides. That's actually because they're incredibly reactive. They will react quite vigorously, and they will do it at room temperature. We call them acyllating agents, and if we have got on this skeletal formula, if that R were a CH3, a methyl group, that would be a carbon chain of 2. So the name that we give to that acyl group is Ethanoil. So it's a slightly different name, slightly different variation on what we see elsewhere. So just with that in mind, what do you think a propanoil and a butanoil group would look like? Well, let's start with propanoil. That's 3 carbons in a chain. So we've got our 1, 2, 3 here. We've got a C double bond O, and we've got the C coming down, bonding to what would be in an acyl chloride, a chlorine molecule. And if we look at butanoil, you can see that it's the carbon chain of 4. Now, acyl chlorides is one example of a derivative of carboxylic acids. Acid anhydrides are another that you're going to have to learn about. Take a look at this and just try drawing out the display formula, or the structures at least, for A, B and C. So hopefully not too taxing there. Ethanoic acid, we can see here with our COOH group. We've got B, ethanol chloride, which is our CH3COCl, and we've got ethanoic anhydride. Now, ethanoic anhydride, we've got our CH3COO, and then we've got a COCH3 down here. But I want to point something out, that if I highlight a key bit here, they're all derived from the same root. On a carboxylic acid, you have an OH bonded to the C with a double bond O. In an acyl chloride, you have a Cl bonded to that same carbon, and in an acid anhydride, slightly more complicated, but what you're actually seeing here, there's a clue in the name actually, is 2 ethanoic acids have combined together. Now, one of them has lost an OH and one of them has lost an H. They go off and they make water, making that a condensation reaction. But we're then left with the remainder of a second ethanoic acid down here. But it's still all of that in the place of either the OH or the Cl. A little bit more of a chance to look at some nomenclature here. So if you try to draw those out, ethanoic acid, the key thing that I will point out here is that we have got, because it's a display formula that has been requested, we have to show every single bond, including the one between the O and the H, which people often forget and just put an OH group there. So that's ethanoic acid. For number 2, we've got our display formula CH3COCl. We've just been looking at these. That one is ethanol chloride. And for number 3, we have got our CH3CO and a CH3CO, so that's our CH3CO2, and they're bonded about the O. And this is ethanoic anhydride that we've already spoken about. When you're looking at the structure of an acid anhydride, my recommendation is to take a look at this section here, and you've got O-coco as a chain, and then you simply have the extension of the carbon chain from each ethanoic acid coming off. So this is CH3C, CH3C, and we've got ethanoic anhydride. Propanoic anhydride would have a C2H5 and a C2H5 there, for example. And remember that when ethanoic anhydride is made by combining 2 ethanoic acids, you end up releasing water, making it a condensation reaction. So ethanoic anhydride right there. Okay, let's take a look at number 4, which is benzene carboxylic acid. So hopefully familiar with the aromatic work from other topics. We've got our benzene ring with a COOH coming off there. And that's alternatively known as benzoic acid. If we take a look at number 5, benzoyl chloride. So the oil allows us to see this is an acyl chloride. We can't have a C double bond O and a Cl coming directly off the benzene ring, so we have our C6H5 and then we add our acyl link on the end, COCl. And finally, benzoic anhydride. So we want to look at two benzoic acids and we get this where we've got our C6H5COO, it's lost an H, and that then bonds with a second one that's lost an OH. So benzoic anhydride would look like this. Now let's move on and take a look at acylating agents. Acyl chlorides and acid anhydrides are actually both very good at this because they have a readily available leaving group. In ethanol chloride, we're going to lose the Cl-, and in ethanoic anhydride, we lose the entirety of this here, which is, in a sense, replacing what the Cl is in acyl chloride. We're seeing the similarities between the two. The type of mechanism we undergo is nucleophilic addition elimination. Now that might sound a little bit like substitution. But substitution, one thing displaces another. Here we add and then we eliminate from an intermediate. So if we take a look, we're going to start to do quite a lot of work with those nucleophilic addition elimination mechanisms. We're actually going to look at 8 variations of this across the 2 types of acylating reagent. So let's start with this one. Let's start with ethanol chloride and water. You've got here the reactants and you've got the products. We know that it's nucleophilic. That might help you to decide on how the reaction starts. We know that there's an addition, then an elimination. So with all of that in mind, can we actually reason out what the mechanism would be? What would be the journey through this reaction? But let's start by drawing our 2 reagents out. I've got my CH3COCl and I've got my water. It's really important you'll notice here that I've added my lone pair on the O because that is going to determine where the attack will be. It's nucleophilic, so that lone pair is going to attack the carbon. Why will it attack the carbon? Because the carbon is very delta positive. It's actually an incredibly high delta positive value because we've got a delta negative oxygen and a delta negative chlorine withdrawing electrons towards himself from the covalent bond. Now, as a result of that, I've got 5 bonds around this carbon. That can't happen. So the double bond breaks. And when we do that, we end up with this intermediate. And you can see a number of things that are very, very important. We've got our CCl and our CCH3 bonds have not changed. But my O, because the electrons have moved towards it, I now have a lone pair up there and it's negatively charged. And I now have a bond between the C and the O, where the nucleophilic attack took place. But because the O has 3 bonds around it, we also need this little positive charge. Sometimes people look at this as it's a little bit like a little stick man, and if that helps you to visualize where the intermediate is going to go, that might be quite useful. But we then need the next step. We've got 2 marks so far. In fact, we've got 3 marks so far. 1 for the first arrow, 1 for the second arrow, 1 for the intermediate structure. To get the next mark, we need all remaining arrows, and this is what we're going to see. I actually know that I still have a double bond here, so that's going to be regenerated. So these electrons shift back round and they're going to reform the double bond. The problem is that we've now got 5 bonds around that carbon again. So we break the CCl bond and those electrons move to here. So you can see there is a sequence. We're losing the chlorine because the double bond has been regenerated. The next one is happening in isolation. It's not stable to have the OH2 with the positive oxygen. So what we see is that one of the OH bonds breaks and the arrow shows the movement of electrons back to the O. That's removing the positive charge, but it's also removing hydrogen, leaving us with the OH group that we know we're going to get. Acyl chloride plus water will make a carboxylic acid. So we've got the C double bond O, we've got the OH, and we've got the CH3. But actually, if you also take a look, we're going to have a secondary product as well. We're going to have HCl. Let's have a look at why and where that has come from, just so we can be really, really clear. Well, the H is what we have lost here. We've actually lost it in the second stage, not where I've highlighted, but you can see that this H is being released when the electrons move back to the O. And the chlorine is being removed, again, actually in the second stage, when the electrons move towards it, just here. So that's one variation of a mechanism, but there are 4 different versions with acyl chlorides, and less commonly that you're likely to be asked about, we're going to do the same with nucleophiles with acid anhydrides. But bearing in mind everything that we've just looked at, I'm going to recommend again that you pause and have a go at doing the mechanism. This time, still ethanol chloride, but not with water. I want you to do it with ethanol. So, the key to this is thinking about how to draw the nucleophile for me, because if you do that, it can make the rest of the mechanism much more similar to what you already know, much easier to remember the key details. I've got my ethanol chloride. I've written out I've actually done methanol there, so we'll do it for methanol rather than ethanol, but the same principle applies. But I've drawn it in the same structure as I had my HOH. I've just replaced one of the H's with the methyl group. So I have got my first arrow going from the lone pair to the carbon, causing the double bond to break, taking us to this intermediate stickman figure type structure. From here, I've got 3 more arrows, all 3 of those needed for the 4th mark. Remember, this arrow is a mark, this arrow is a mark, the intermediate structure is a mark, and the arrows, we're regenerating the double bond, which causes the chlorine to be lost, and then we are losing not the OCH3 bond, it's going to be the H that we lose. So these electrons come in, and we are left with, in this case, we're left with an ester, because we've now got a COOC. But we're also still going to make HCl, and we're making HCl because we are losing the H that you can see here and the Cl that you can see here. You can also see, actually, that the OCH3 that is on there has come from the OCH3 in the methanol that we used just here. So hopefully we're starting to build up an idea of how we get to these structures. You might also want to be thinking about what considerations we might need to make about this being produced as a secondary product. But while you do that, have a go at the 3rd version of this mechanism, this time using the nucleophile ammonia. Now what I'm hoping is you're getting into a little bit of a routine here now. We've got ethanol chloride, we draw that out and we draw our ammonia. Straight away, I've put my lone pair on there, so I know that my lone pair is going to attack the carbon. Remember, the carbon is very delta positive because it's bonded to a very electronegative oxygen and a very electronegative chlorine that are going to withdraw electrons away from the carbon. So I've got 1 mark, I've got 2 marks. That takes me to my intermediate, not quite a stickman now, but you can see that we've formed the CN bond. The N is positive because we've got the extra bond around it, and I've got my O- at the top showing my lone pair. Now from there, exactly as we have seen before, we regenerate the double bond. Once we've regenerated the double bond, that forms 5 bonds around the carbon, so we need to lose the chlorine, and then we lose one of the H's from the NH3. Now that is going to take us to what we see here, which is an amide, something that you will see in the amine topic, and you'll learn more about the naming of those in there. But we're also making HCl, and again we can see that we're losing the H in the ammonia and we're losing the Cl from the acyl chloride, and they're coming together to make HCl. Three of them, all with huge similarities. And there is a fourth. So let's take a look at that. Instead of ammonia, let's do the same with the nucleophile methylamine. So my acyl chloride is drawn out, my methylamine is, and you can see the structure that I've drawn it, keeping it as similar to the others as I can. My lone pair on the N, absolutely vital. Arrow number 1, mark number 1, I have a nucleophilic attack of the lone pair on the N to the delta positive carbon, causing the C double bond O double bond to break, giving us an intermediate that we're now really hopefully quite familiar with. At this point, I've got 3 different things that are going to happen, 3 different arrows to add. I regenerate the double bond, which causes the chlorine to be lost, and you can see the arrow there, and I lose one of the H's from my amine going back to the N. That is going to take me to an N-substituted amide. Again, you will learn a lot more about those in the amine topic. And once again, just as we saw in every single version of this, all 4 of these mechanisms, HCl has been the secondary product. And we can see a little bit about where the structure has come from based on the reagents that we had. Now, less common, but we are going to look at those 4 nucleophiles again, but instead of with an acyl chloride, with an acid anhydride. So, ethanoic anhydride and water. Have a go at this mechanism. Try and apply everything that we have just done to see if you can make sense of it. Well, in the first instance, I'm going to draw out my ethanoic anhydride. There's my O-cocoa linkage, and I've got my CH3s coming off, and I've drawn my water below. Now, the water is going to attack the delta positive carbon, just as it did previously, and that's going to lead to the double bond breaking between the C and the O. And that takes us to an intermediate. Now, this looks a little bit more fiddly, but exactly the same principle applies as it did with the acyl chloride. It's simply that the Cl has been replaced by an OCO-CH3. So we end up with this. And once we've got to here, again, exactly the same as we saw with the acyl chlorides. We regenerate the double bond. Here we're not losing a chlorine, we're losing where the chlorine was in the acyl chloride. So our OCO-CH3. Or a CH3COO minus ion. From there, we're also going to have to sort out this positive oxygen, so we lose our bond between the O and the H, the electrons go back in, and that takes us to CH3COOH. That's what we've made as a result of the mechanism. But we've also made ethanoic acid as the secondary product. Now, technically, that means there isn't a secondary product here. But CH3COOH will be the secondary product whenever we do this mechanism with an acid anhydride. And again, let's have a look at why. We're losing the H from our H2O, and we're taking our CH3COO minus from what has been lost in the second stage of the mechanism. And again, you might want to be comparing this secondary product with the secondary product that we saw in our acyl chlorides. Okay, we're going to move on and we're going to look at the reaction this time with ethanoic anhydride and ethanol. So it's exactly the same principle as we saw with acyl chlorides. See what you can do. And you can see here that we've got our acid anhydride, ethanoic anhydride drawn out. I've drawn my methanol in the same format as I did with water, so the mechanism, you can see just how similar it is. My lone pair on the O will attack the delta positive carbon. That will cause the double bond to break between the C and the O, giving us an intermediate that I'm hoping you're really now quite familiar with. I've got my C2H5OH at the bottom, the positive on the O. I've got my O- with its lone pair here. And we know we're going to regenerate the double bond, and we know we're then going to lose our CH3COO- up here. We're also going to break the OH bond here as those electrons move back to the O. So in this case, what we're actually making is an ester. Actually, with an alcohol and an acyl chloride, we made an ester. So the nucleophile will determine what the primary product is. But the secondary product, again, is ethanoic acid, just like it always will be with an acid anhydride. So we can see where they are coming from. Our H and our H plus and our CH3COO- coming together to make that secondary product. And you can also see the OC2H5 from the alcohol has become the extension that's made it into an ester. So let's move on and look at the same one with ammonia. I've got my acid anhydride and I've got my ammonia, exactly the same as we've seen in all of the other examples. Lone pair attacking the carbon, break the double bond, giving us this intermediate. I've got my O-, I've got my NH3+. My O- can't be sustained. I'm going to regenerate the double bond, which means I'm going to break off the entirety of what's at the top. I'm also going to lose an H from my NH3+. Those electrons are going to go back to the N. In this case, just as we saw with ammonia with an acyl chloride, we're making an amide. And just as we always see with ethanoic anhydride, we're making a secondary product of ethanoic acid. Again, colours here, just so you can see where they are all coming from. And now let's look at ethanoic anhydride with methylamine. We did methylamine with an acyl chloride, exactly the same principles again. Here is our ethanoic anhydride and methylamine. My lone pair on the N is going to attack the delta positive carbon, break the C double bond O, taking us to the hopefully now incredibly familiar intermediate. I rebuild my double bond. I lose my CH3COO- and the CH3NH2, we're going to lose one of those H's and the electrons move back to the N, removing that positive charge. In this case, just as we saw with an amine with an acyl chloride, we're making an N substituted amide. And as a secondary product, as we always get with acid anhydrides, we're making ethanoic acid. And again, you can just pause this if you want to take a look and see precisely where the different bits of the structures began and ended up as part of this mechanism. Now, to finish off, a couple of questions. In industry, would you favour the use of acid anhydrides or acyl chlorides in these reactions? Now, depending on what you've said, it could be that you've gone for exactly what we're talking about here, but there are certainly advantages for both, and we will discuss them. Actually, in industry, the favoured choice is acid anhydrides rather than acyl chlorides. And you might be thinking that's a little bit odd because I was talking about how incredibly reactive acyl chlorides are, to the point that those reactions will happen at room temperature and they are incredibly vigorous. But actually, that feeds into the reason why in industry they do actually opt for acid anhydrides, and I'll explain why in a moment. The first answer you can give here, though, is acid anhydrides are cheaper. So that's a definite advantage. You're lowering your production costs. Acid anhydrides are actually much less corrosive as well. And that ties in with that level of reactivity. Remember, acyl chlorides, the high level of reactivity is because you've got an incredibly reactive or an incredibly delta positive carbon because it's connected to a very electronegative oxygen and a very electronegative chlorine. That has more of an impact than you get with the two CO bonds in acid anhydrides. So it's less corrosive. It's a less vigorous reaction. Now, actually, that does mean it will happen more slowly, but it also means it's happening more safely. So we are thinking acyl chlorides, it could be an incredibly dangerous reaction to do. So acid anhydrides takes that danger away. Final component to this answer is thinking about that secondary product. The secondary product is ethanoic acid with acid anhydride, so that's vinegar, it's a weak acid. Whereas with the acyl chlorides, not only are you making HCl, a strong corrosive acid, but because it's such a vigorous reaction and it's so exothermic, you're actually going to form fumes of HCl. So we're thinking about actually there's dangers of inhaling HCl fumes. We're thinking about the higher temperature. We're thinking about the extra damage that could cause, the greater vigorousness of reactions when something's gaseous rather than liquid. So for all of those reasons, we would use acid anhydrides. So that takes us to the end of quite a big component of this topic actually, but a very important one because those mechanisms are absolutely fundamental to what we're looking at within here. It also brings us to the end of this topic though, so thank you for listening and goodbye.